So the next thing I want to talk about is scatter plots. So when we're comparing two different variables, right, our independent variable and our dependent variable, we need to have a way to represent these, okay? And one way we can do that is with scatter plots. These are also called scatter diagrams, just as a friendly reminder. So a scatter plot is a graph in which paired sample data values are plotted on points, right, with our x values and our y values. So again, x is our independent variable. We call this our explanatory variable. Y is our dependent variable. We call this a response variable. And we plot this on our vertical axis. So what we're doing is we're taking essentially the ordered pairs, so the groups of x and y of our data values, and we are making a scatter plot. This isn't a very nice line, right? But we're making a scatter plot. So this is an example of a scatter plot. So, for example, how would we create a scatter plot for the weight and price of diamonds? Okay, do we expect diamond price to depend on weight? Well, yeah, I think it would, right? The bigger the diamond, the more it would cost, wouldn't we think? So here we have our data. You can pause this and take a closer look. Let's go ahead and look at the scatter plot of this data. So here I have my scatter plot of my data, right? So I've got weight, and I've got is my x value, my independent variable, and my price is my y value, my dependent variable. Looking at this graph, does it appear that weight, that the only factor on the price of diamonds is weight, right? Look, I have a 1 carat diamond here that's, maybe I shouldn't use blue because I already graphed in blue. That's a little over 4,000, but I've also got one that's almost 10,000. Could there be some other underlying factor? So one of the underlying factors that affects the cost of diamonds, which we can see in the previous slide, is also clarity, right? The clearer, the prettier the diamond, the more it's worth. So there is another factor involved in this scatter plot. So there are several types of correlation. The first correlation is going to be positive correlation, okay? This is when the data values of y increase with the values of x, okay? So as we can see in A, it looks like our values are going up a little bit, but not a ton, right? So this is what we would call a weak correlation. Same thing here. We're getting a little bit stronger. Okay, we've got an R coefficient of 0.7. Note, this is not slope. Our R value, our correlation coefficient, is not slope. Okay, so this is a little stronger. And then up here we have R equals 1. This is really strong. This is perfect correlation. This is never going to happen in real life. Okay, so we've got positive correlation. If we've got positive correlation, we've also got negative correlation, right? And negative correlation, our data values appear to be going downhill, right? As y values decrease, as x values increase, okay? And our correlation again gets stronger as we go from D to F. F is perfect negative correlation. Again, perfect correlation doesn't happen. It will not happen in the natural world. It might happen in your textbook. That's the only place, okay? Another option is that we could have no correlation, right? There's no way for me to draw like a nice line through this data, right? There's no correlation. So this would be x and y doesn't appear to be linked in any way. This could be the data of your height and your GPA, right? There's no relationship between your height and your GPA. We can also have a nonlinear relationship. So x and y in this case appear to be related, right? They go on this nice little curve. But the relationship doesn't appear to be a straight line. So nonlinear correlation. So we've got positive correlation where variables increase together. Negative correlation, while one increases and the other decreases. There's no correlation, or there's a nonlinear relationship, right? They follow a pattern, but it's not a straight line. How do I measure the strength of a correlation? Okay, so we measure this with the correlation coefficient. That's our R. This correlation coefficient is not slope. I cannot say that enough. It's not slope. So our R value goes from -1 to 1. Okay? If there's no correlation, our value is going to be really, really close to 0. Okay? Values close to 1 mean a strong positive correlation, and positive values closer to 0 mean a weak positive correlation. So that's like 0.3, 0.2. Strong would be 0.9, 0.75, because we could have 2 decimal places. Why not? Values that are close to -1 mean there's a strong negative correlation, and values closer to 0 mean a weak negative correlation. So like -0.1, -0.04. Okay? It's important to note that even though these graphs will have a correlation coefficient, even if they have strong correlation, that does not imply causality. Okay? Correlation does not imply causality. So, again, if we have positive correlation if our R value is between 0 and 1. Both of our variables will increase together, right? X increases and Y increases. If a perfect correlation, R equals 1, this does not happen in the real world. It may happen in your textbook. If there's negative correlation, my coefficients are between -1 and 0. When one variable increases, okay, so typically my X, then the Y value decreases. Okay, a perfect negative correlation, all points lie on a straight line. It would have a correlation coefficient of R equals -1. Again, this will not happen in the real world. So, figure 7.5 shows a scatter diagram for the variables of number of farms and mean farm size in the United States. So each dot represents data from a single year between 1950 and 2010. Okay? The early years are on the right and the later years are on the left. So let's estimate our correlation. Oops. That's all I want us to do is estimate it. Okay, so this is not a perfect correlation, right? I can kind of draw a line through it. It's definitely negative. They're pretty close to this line, so I would say that's a stronger correlation. So I would say it's like -0.8. That's it. That's all I want you to do is estimate. I will accept anything from like -0.7 to -0.99. Here's what I want you to show me. I want you to tell me that the correlation is negative. I want you to tell me that it's strong. And then I want you to guess what your R value is. That's all this question is asking you. Okay? No calculations involved. Use your gut and your knowledge that you have gained from the earlier slides. Okay, let's take a look at the effects of outliers, right? Remember, our mean is affected by outliers, our standard deviation is affected by outliers. That was a question on our last exam. Okay, so if I calculated my correlation coefficient of 0.88 for this data set, what kind of correlation is this? Well, this would be positive correlation and strong, right? 0.88 tells me it's a strong correlation and it's positive. My question is, does that look like this graph over here? What happens if I cover the data point in the upper right corner? So I'm asking you to do that. Try not to pause the video accidentally, but cover it up. Okay, if you cover up that point, which I can't erase, but I could like X out, I guess. Ignore this point. If you ignore this point, what happens to our correlation? Well, our correlation becomes basically 0, right? There's no correlation here. So it's important to remember that we still have to worry about the effects of outliers. All right, let's take a look. So this figure shows the scatter diagram collected by a consumer group studying the relationship between the weights of prices and the weights of cars and their price. Okay, so cars are not typically something you buy by the pound. That would be like bananas or potatoes, right? But let's look at this. So let's look at this relationship between car weight and price. So the data set as a whole kind of shows us this positive correlation, right? But that doesn't seem to make any sense, right? We wouldn't pay for our car by the pound. Let's go ahead and ignore the whole group, and let's look at each cluster. So if I divide this graph up and I just look at each cluster, if I look at the lower weight cluster over here, this is my car, this is my little Chevy Aveo. Chevy Aveo, that was the first car I owned. I have a Ford Fiesta. Oh, being in this house is getting to me, guys. Okay, so it appears that there's no correlation, right? And that would make sense, right? Tiny little cars, little compact cars like mine tend to cost less, especially if they're used, right? Than like a truck or an SUV, which is going to weigh more. This also appears to have no correlation.